Hello and welcome to our talk integrating the fabulous embedded FPGA framework into the RISC-V ecosystem. That's work done by Nguyen, Bea, Jing, Kelvin and myself from the University of Manchester. What is the fabulous framework offering? It's a fully integrated open source embedded FPGA framework which uses a lot of tools and algorithms under the hood to provide good area of and performance measures. It's entirely open and free, including commercial use, and it integrates a lot of other open source projects. It supports custom cells if provided, for example, for configuration storage or switch matrix multiplexes. But however, if you don't provide those, we can fall back to standard cells if needed. It supports partial reconfiguration, something that's very useful for embedded FPGAs, but that you don't even get from a lot of industry offerings. It's designed for ease of use, while it provides you full control over all aspects of the flow whenever it's needed. It's versatile in the sense that you can use different flows for the ASIC implementation as well as for the Verilog or VHDL to bitstream compilation. And that includes open source tools for all aspects of the flow, but also industry tools like Cadence or for example for the ASIC implementation. It's easy to customize and it allows you to integrate your all IP inside the fabric, but also the fabric can be designed in a way that it's easy to integrate with the rest of your SoC that you may want to build. Okay, a little bit a closer look at the fabulous framework. Here the whole figure shows kind of all the different blobs and pieces. It's a little bit busy. We don't have to go in all the details. Here at the top left, you basically just provide a fabric description, which could be as simple as a spreadsheet where you define the tiles you want to use and therefore the layout of your fabric, wide in terms of, let's say, logic tiles, DSP blocks, memory blocks, and so forth. And then Fabulous will take care about all this to generate you the RTL code and constraints to drive ASIC tools, yeah, all the way through the GDS that you can send to your fab in order to get your chip. At the same time, Fabulous is also generating models to parameterize open source tools that you will need to compile your Verilog or VHDL all the way to a bitstream that can then run on your FPGA fabric. We also provide the generation of simulation models that you can run in Verilater, yeah, or ModelSim if this is your preference. We even generate emulation code that allows you to emulate a fabulous fabric on a commercial FPGA, like for example a Xilinx FPGA. We tested this with various fabrics so far, and we provided, for example, some Vertex 2 or Lattice clones, which are all for which patents are all expired at the moment, so we can consider those fabrics basically as public domain. If you want to learn more about the Fabulous framework, I refer you to our FPGA 2021 paper. Okay. Basic concepts on an FPGA. An FPGA is basically built from small tiles, yeah, with some tiles implementing logic, other tiles may implement I/O. You may combine multiple tiles to form bigger, more complex blocks, for example, for digital signal processing applications, or maybe your own machine learning block, memory block, whatsoever. Yeah, and you stitch this together into a regular fabric, wire this somehow together, provide switch matrices to connect different blocks together, and that is fundamentally forming reconfigurable hardware. Okay. A slightly more abstract view on the same figure that I had before is just looking at different blocks, and the way you can specify this in Fabulous is really as simple as providing a spreadsheet for that one. And Fabulous will take this spreadsheet and compiles it actually into a fabric. Yeah, and each tile here that or cell here is nothing else as a descriptor for the corresponding tile. Yeah, and if you want, you don't have to. If you want, you can go into those tiles and customize them, change them, provide your own ones. And to give you an idea how a tile looks like, it's nothing else as yeah, a regular tile that provides wires to the surrounding, it provides a switch matrix, and it provides primitives. Yeah, and the primitives could be everything like a lookup table, could be a slice as in Xilinx terms, it could be a multiplier block, could be a small memory block, could be anything like that, yeah? And if you want to specify your routing, you just say how many wires you want to have in your northeast, southwest direction, yeah, give them symbolic names, and you can also specify adjacency matrices or lists or something which is not shown here for simplicity. Okay. Yes, now with knowing how to specify fabulous FPGA and integrating it, why should we go for embedded FPGAs? Well, it allows you to customize your chip for multiple different applications, yeah? A lot of embedded applications are quite specialized, and you may not want to build a different silicon for each different application that you may want to have. And you may want to have more like a standard chip that you can customize for different scenarios. Yeah, like for example, if you have a sensor, you may want to implement a dedicated trigger, right? Or you may have different signals that you may play with or use, yeah, that require different compression engines. You may have different protocols depending on what peripherals you attach, and so forth, yeah, and FPGAs allow you to build corresponding programmable translators for those ones. It's also interesting that it provides you in field updates, yeah, so in case something goes wrong or in case you figured out how to do something better over time. But it's also an option for after sales business where you may sell features later to customers even after the chip had been manufactured. And it's ideal for basically plumbing, all kinds of accelerators, and custom instructions. And for the latter one, I have a nice motivation, which is here in the bottom. You see different ARM architectures and the number of instructions they provide over the different generations of ARM instructions. And what you see is basically that the number of instructions that you add to your CPU or to your instruction set architecture is kind of exploding over time. And the way I like to visualize this is with this Swiss Army knife. And if you really think about it, the more instructions you add to a CPU, the more underutilizing the more you underutilize your FPGA, your CPU, because at one point in time you can only basically fire one instruction or a few instructions, right? So this gets all very expensive, and you have to keep in mind that on a RISC CPU, because nothing is really micro-coded, each extra instruction costs you real estate in terms of area, may slow down things, and so forth. Yeah, and then you have all the legacy requirements that you may be able to add instruction, but you may not be able to remove an instruction easily. So having a very lightweight core and adding, for example, reconfigurable custom instructions is indeed a very attractive opportunity. And a system that does this, that's just currently taped out and under production with Skywater, is our Fuse RISC chip that was done by Andrew Atwood. Yeah, and it is a dual RISC-V chip with embedded FPGA. This here in the middle, this is a fabulous FPGA fabric. Left and right, there are two cores, and here these are the memory blocks from OpenRAM. And it's a relatively small fabric with just 800 lookup tables and a couple of DSP blocks, but it's still sizable enough to do reasonably good acceleration. You can have multiple different instructions. They can even be located at different positions. And in our case, it can be even the same bit stream that can run at different positions. That means also that you can really have multiple instructions running. And while one instruction is in use, you can reconfigure other parts of the FPGA basically in a hot swap manner. Both FPGAs here provide their, both RISC-V cores provide the operands A and B to the fabric, right, and multiplex from different regions results back into the register file. And both sides can do this, and both sides can use the FPGA fabric either exclusively, partially, or even joined together. We have different configuration options. One core is able to configure the fabric through Wishbone. Otherwise, we have serial links to the outside world to configure the chip. And as I said before, the configuration itself is partially possible. Yes, I hope that gave you a little bit of an impression what you can do with fabulous frameworks in a RISC-V world. And with this, I want to just give you one short slide at the end where we compared Fabulous with OpenFPGA, which is another open source FPGA framework. Both frameworks aim at basically have similar objectives, and both frameworks had submitted a fabric to the last Skywater 130 nanometer process. That means we can really do an apples by apples comparison, as both really use the same framework, have the same constraints, right? And the fabrics had been basically the same. Both had been 4-bit lookup tables, clustered in CLBs with 8 lookup tables each. The physical implementation problem is round about the same. And this blue bar here in the middle, that is the one that we taped out. And for that one, we had been 17.4% smaller already as OpenFPGA. And since then, we did some further optimizations that gave us another 20% in area optimization, and the optimizations themselves are described in our 2022 FPGA paper, if you want to see more about it. Okay, and with all these optimizations, we are getting now to north of 90% core utilization. So that's actually getting as good as it can be. And the fabric itself is really, really useful. And we had been able to implement a RISC-V core on our fabulous fabrics. Okay, with this, I just want to say thanks to all the people that make this work possible, all the contributors here, all our sponsors, including EPSRC with the Forte program grant. I also want to say thanks to Google and eFabulous for supporting us with tape outs. And last not least, to all the other great work that is done in the open source tool work to make this work possible. Bye.